Hello everyone, this is Fabricademy 2019, class 12, Soft Robotics with Lily Chambers and Adriana Cabrera. I give the word to you. You can start sharing your screen. Yes.
Thank you. Oops, start right from the beginning. So, welcome. I'm very excited to be with you here at Fabricademy. Today's class is about soft robotics, and we're going to start with a bit of an overview about what soft robotics can mean in sort of a robot terms, and quickly we'll get down to artificial muscles and then the materials themselves. So Adriana and I are going to talk about inflatables, molding and casting, actuators, and sensors. I come from a background of marine biology, and I segued into engineering and developing materials. And at the moment, love to work with soft robotics in terms of actuators. Now, what is it about nature that's so enthralling when it comes to thinking about squishy, soft, movable stuff? Well, it's that nature is, in essence, soft, sustainable, can be quite robust and flexible. I have a picture in the middle there, which is a hagfish slime. So the hagfish is in a bucket, and the researcher is pulling up the mucus, the polysaccharide glycan gel that's created from this hagfish. And on the left-hand side of that slide, you'll see what are called skeins, and they look like thread filaments. And these are secreted by the animal, and they rupture when they go into seawater, and they unravel, grabbing all water around it to make this really interesting sort of thick materials. It's just an example of another type of fiber that's out there that's already made and functioning inside the animal that it can use when it needs to sort of create extra structures. In this case, it's a defense mechanism. So it does that, creates a massive mucus slime, and it can escape. And on the other side, I have sort of the plants and their ability to intertwine with already formed structures, use them to their advantage, as well as, of course, the sustainability. So you can chop a piece of grass and it will continue to grow. That won't be the end of it. So in terms of biomimetics and nature and allowing these things to be a part of our system, the key thing is to think about moving away from persistent and getting into something biodegradable. And that's where my research is really interested in developing something that can move us from batteries towards, let's say, stomachs or soft muscles or soft bodies. And the really interesting thing then is to have that go back again. So, okay, we want to make soft, squishy robots. But one of the really interesting things is that our own natural muscles, for instance, in our arms, etc., can only really provide us with contraction. So those muscles, if you took them out of your body and you just had a look at them, they just contract. They need some sort of antagonistic system to actually get them to move in the opposite way. So for any expansion to occur, you have to have a whole other system. Whereas in artificial muscles, we can start to create a system where you can have contraction expansion in the same thread or the same form, and also introduce things like torsion, twist, rotation. So I think technology has a lot to offer back in terms of coming up with new actuation. So if we look at actuation and sensing, there are many different ways to do that. And here's the nice list to sort of consolidate our thoughts. So for actuators, they can be actuated using fluidics, electrics, thermal, magnetic, chemical, biological, and also then hybrid systems. I'm going to briefly introduce the biological one today because I think that's quite an interesting sort of new development in terms of these actuators. Okay, well, I saw already some of your projects are going to be incorporating sort of pneumatics or some sort of expansion modular systems, and a really nice place to start here with pneumatics or with fluid actuated robots is having a look at these PneuNets. So this is a really nice piece of research which is looking into basically using silicon using cast molds and creating two layers. One which is going to have the shape, the troughs of those little indentations you see, which are going to trap the fluid we're going to pump in. And then you have a strain limiting layer. So in that's graphic A, layer 2. That's the strain limiting one. So you have to create a layer against which all this is going to do some work. In section B there, you can see the grooves. And if you look a little bit further over to the side, you have this PO and P1. Well, that's where you have the atmospheric pressure versus an internal pressure that you're going to force in, air, or whatever else you're going to use. And with this, they really got a really interesting multi-gate robot, which can move around just with compressed air being pumped into the different legs and arms. So PneuNets are a really sort of wonderful way to explore fluid-filled actuators. If we expand that out to what is happening at the moment in terms of robotics and robotic arms, here's a company called Pneubotics, which has developed sort of industrial-sized robotic arms to be able to lift things and put them down, but completely made with, you can see there's stitching and hinges that are sewn in, and it's all filled with air. So why the revolution here? Well, this is really an interesting way to work with humans. There's no safety element issue. If this robotic arm swings or if you're interacting with it, you can't get hurt like you could from a rigid robotic arm. And also then it doesn't have to be stuck behind a cage and isolated away from the human environment. A really neat one as well that I think Adriana is going to expand on for us, don't mind the pun there, is foam, or this fluid-driven origami-inspired artificial muscles. And this work, it's really fascinating because it's exploring both creating a skeleton, a skin, and filling it with fluid. So I've left it in the fluid-driven side of these actuators. And you can see there that it can lift quite a heavy load. So this thing can sort of have a 90% contraction, and it can also do something pretty interesting as well, because you can play around with the different materials. Part A up in the top picture there is actually made from PEEK, polyether ether ketone, and so it can biodegrade if you use it in sort of different liquid mediums. So you could have an actuator which could be biocompatible, maybe for medical or wearable applications. You've also got, the issue with these is you are using compressible air or other fluids pumped in and out. So these are not easily mobile. On the graphic on the right-hand side there was lifting the tire. This is really interesting because you're sort of getting peak power densities of over 2 kilowatts per kilogram, which is pretty substantial in terms of being able to move something. I've also shown in the bottom left-hand corner there a self-folding structure by the same group at MIT. There's a really interesting where they're using the paper origami, which is heat sensitive and is in a single motion, will sort of self-fold in on itself and be able to actuate and move around as a fully functioning robot. And that's Daniela Roos there at MIT. And there's a whole side to that too, which is small scale robot rather than the actuators of this larger scale sort of actuation motion that we're seeing here. The interesting thing about doing something like this where you're using origami is it doesn't have to be limited manufacturing wise. You can do quite large scale things with it. You can start to think about low cost artificial muscles so you don't get trapped into using sort of fancy materials. And with that, you can get lots of different motion regimes as well. So you can not just have sort of expansion contractions, you can work in different forms. Okay, so fluid-driven actuators. So we've shown kind of how you can have a whole robot system, but also you can think about this in terms of exoskeleton, trying to manipulate or offer some sort of flexible dynamic support system for arms, hands, legs, etc. Is a really interesting sort of application, obviously, of soft robotics. And here you can see the tubes coming off where the air is being pumped in to something like that with the PneuNets, where you have very specific chambers being filled with the fluid. Another couple examples I want to show you just to give you some scope for an actuator like this is Furl, where you're seeing large-scale sort of architectural structures which allow the kinetic responsiveness of whatever's happening in the environment, whether it wants to cool the building, or for instance, provide a different shape. It can do that with these very large pavilion scale actuators. Aposema in the bottom there, you can see is a soft robotic mask made of the Soft Robotics Toolkit. There's some information available on there, where it was placed over the user's face, and using small force sensors, the difference between smiles and frowns were used to be able to kind of provide an emotional response to what was going on. So with the colors would change, bulges would appear, etc. So a really sort of interactive feature there with those molded channels and colors corresponding to the emotive state of a person. And now down to sort of the first full body soft robot. And you can see, so the first published out there, sort of 2016. So we haven't been able to actually generate full soft robots in all of their capability because we've been restricted by the hard materials that are paramount in the development of, let's say, battery styled or motors. And here's a really beautiful example of that. This one works in a really interesting way. The chambers that you see there in the colored violet are actually little reaction chambers. So it's an interesting printed structure where it leaves flecks of platinum around, so that if it uses a little fuel pod of hydrogen peroxide, so a little bit of rocket fuel going around, when that meets the platinum flakes that have been embedded inside of it, you have a gas reaction, which allows the arms to flick and twitch. And they've got this to swim in a liquid medium too. So this has a lot of inspiration, obviously, from the octopus in terms of it being movable, flexible, and moving from spaces through small spaces. And here you have an example of something which doesn't need cables and wires or anything hard to go with it. At the moment, I believe it gets something like 4 to 8 minutes of movement, which is pretty incredible. And obviously you could change the payload of the fuel, etc., to modify its use. But as a sort of an inspiration tool, this has a lot of interest. Another chemically actuated one that's of interest here is sort of pneumatic hydraulic system incorporated as well is MORPH. So it's a microfluidic origami for reconfigurable pneumatic hydraulic system. And here this was all done with lithography, which is a really interesting way to think about stacking. I think it's about 12 layers go into the structuring of something like this. And by developing a new hybrid technology that merges 3 different fabrication techniques that they had, they made a soft robotic spider of silicon rubber. And it's really nice. They've got the colors in there to be able to show you the different structure and motion that can do, but obviously the scale is a key thing there. So we're on a teeny tiny scale there. The Australian peacock spider is the inspiration for this one, and it doesn't, obviously sometimes when biology gets transferred, it isn't so important, what the final aspect of it jumps like a spider, etc. But the way of the sort of interconnectivity between the arms and the movement that it can get is key here. So one that I'm really keen to highlight in this series here is this idea of using active fluids, or fluids with biological components in them. So actual microflagellar bacteria have been exploited in these 3D printed micromotors. So they're very, very small. And what they've got here is individual little chambers for the bacteria to slot into, and then using their flagellum actually get them to drive or turn the motors. There's ways in which they can get the bacterium to swim and not swim using sort of light pulses and genetically conforming that so that you can have a response of all turning in a direction, a clockwise or a counterclockwise direction. The use of micromotors then is still more on a microfluidic scale, so maybe not what people are going to be developing right away for products, but I think it has a lot of potential in terms of not just microbes wiggling and creating new motion in, let's say, even in textiles and stuff, but also to think about there are small structures. So this is a graphic showing biological swimmers, but also artificial swimmers. So shapes and size lengths, which when in the small scale flow where you're motion is controlled entirely by things like Brownian motion, so nothing to do with gravity anymore. It's too tiny. You can have some really exciting different shapes which allow for sort of agitated motion, and there might be some possibilities of thinking about how you could drive certain components using an active fluid. So moving a little bit more into the sort of the wearable sensors, here's an example from Disney research where it's got sort of a pneumatically actuated jacket for embodied haptic experiences. And this is where the jacket is going to conform and move in different ways. And they have it set up so it was part of a VR system. So let's say one example was a snowball fight. So the snowballs impacting obviously on the digital screen would be translated into sort of a pressure where they would fluid fill using air and different force sensors. They would fluid fill all of these compartments. This jacket itself, I think, is made up of something like 26 sort of airbags, all interconnected. And the idea here is to give you haptic feedback in a more sort of embodied state rather than, let's say, the vibration that you might be used to on your mobile phone. Another really interesting one is using stretch. So sensors, the fabric stretch sensor by Stretch Sense Limited. And these stretch sensors are actually capacitors. So they're very soft, movable things, but an indentation or a deformation is going to change the capacitance. And if it changes the capacitance, then you can start to have information about how much it's been deformed or what changes have occurred. And the use of these sensors is for all sorts of things. They've got smart clothing, health and wellness, sports and fitness, as well as, same as the last one, virtual reality. But an interesting application of this in the Zozo suit is so that basically you could put on this garment and it would take all of your individual measurements for clothes fitting. So instead of going into the shop and having to try on multiples, the company could send you this, you could put it on, they would have the data to be able to send you the right articles of clothing, etc. So there's some sort of aspect about the user interface as we move towards the digital landscape in terms of buying our clothes online, etc., where this might have a really big impact. And I thought would be of interest to you, those of you in the specifically looking at sort of body form hugging sensors and robotics. Another example that's really interesting that's come out is the idea of wearable sensors in the form of monitoring different aspects. This one is a sweat monitor. So the biointegrated device is made up of 5 distinct layers. What it has there, you can see at the top one is a wireless electronics, so it can chat to your phone, a cover silicon, which covers these little sensors inside in a microfluidic channel. And then it needs an adhesive layer, so it needs some way to actually stick to your arm or wherever it's going to be. The sensors that it's looking at there, you see those 4 different colored dots, are things like biomarkers in your sweat. So it could be pH, lactic acid, what else is in there? Things like chloride. And in doing that, you can really get some useful information for different users. The interesting thing about using the silicon is there are, of course, the sensors and putting them on a flexible substrate is not a new aspect. But what's new is maybe the different type of sensor materials. So sensors on plastic are great, but it's not very breathable. Sensors in fabrics, as I'm sure some of you are very aware of, are very good as well, but it has low sort of chemical resistance, and it wouldn't create necessarily maybe the surface-to-surface interaction that you might need for a sensor to work. So finally, things like silicons are kind of ideal in that sense because they allow for really good skin contact, as well as then being able to move with your body. Yeah. So the idea then of allowing the data to follow you in real time is obviously a very powerful tool in terms of health. The other one from Disney Research that's of interest is metasilicons. Injecting basically, so using all your same sort of silicon-based, let's say actuators or robot, you're creating your full body structure, but then use the insertion of different materials to create a sort of graded mechanical response. So a really interesting thing would be, let's say, for instance, you have your silicon, you could inject it with harder silicon, like a harder shore silicon, to create a stiffer substrate, or you could inject water to make it less stiff. And in doing this, you could start to really play around with different mechanical components. There's a lot of work out there at the moment as well on looking at the spacing and the interstitial spacing, where they should go to be able to give you the mechanical response that you might like. So thinking about sort of hybrid things where you're mixing the materials in. And finally, then I wanted to also highlight the one you've probably seen many times, which is the coiled nylon threads. This is one that we like to play with in the lab a lot. This is an off-the-shelf fishing line nylons. It's not fancy. You can get them for a few euros. And the very simple coiling of these can provide you with sort of 10 to 15. You can get up to sort of 20% and higher if you do further processing like annealing, where you're going to heat them up. But you can actually, without doing any of that, you can actually get an actuation just from building them yourself and having a play with a hairdryer to actuate them. These are sort of thermomorphs. And what's happening here is that you're getting the different coil with a twist insertion. You're allowing there to be movement and play in response to thermal actuation. So a very sort of fun thing to play with. On the top there is just an example of how you can do it. So you can attach one end to a drill, the other side to something secure like a hook or a little vice clamp, and just twist it. And as you allow basically the twist to propagate, you can slowly control with your hand movement towards and away how thick you want that to be, how long you'd like it to be. And then finally in the bottom there, that video is a really good example of a sort of a material being created with this. So some nylon you could just do, or polyethylene you could use just from off the supermarket shelf. But if you wanted to get a little bit higher actuation rates, you could use something that already has a silver thread inside of it, so that you could electroactivate it. So you could heat it up and cool it down by using a power supply. So those are what's happening for the ARC electromaterials there. And they have then many of the fishing line nylon threads coiled up together, and interwoven in between them then is lots of yarn. So that's a really a synchronized response then to heating and cooling down. So it might be something well worth looking into. Another part, as some of you are very capable with your electronics, some that might be worth looking into are these electroactive actuators. There's two main groups. There's sort of ionic electroactive polymers, and there's field activated electroactive polymers. Both take an electrical input. The ionic EAPs are a bit friendlier to work with because you're in lower voltages, whereas the field activated EAPs can need kilovolts. So obviously it needs a lot of sort of health and safety restrictions around those. But ionic metal polymer composites are basically sandwiches of materials. You have electrodes with a polymer membrane in between, sandwiched in between. And you can you're applying the electrical current across the two electrodes. When you apply a potential, you're causing the cations to migrate across to the cathode, and you get this swelling going on, so you'll get this natural bend. And also then you can have that in reverse. Once you remove the polarity or you reverse it, you have the flow in the opposite direction. And in doing this, you can get really nice actuation movements. Dielectric elastomers, typically pretty high voltage is required. But here I'm showing the sandwich between the arms, the two electrodes, and the voltage off. When you put the voltage on, then you get this squishing of that dielectric elastomer, and the dielectric elastomer has to move out of the way, so it gets sandwiched out. the filling basically gets moved out, and you get very large actuation strain rates for materials like this. The equation I put on there because I think it really helps illustrate what's happening there. So when you're talking about this sort of electrochemical pressure buildup in your system, the things that you're going to be playing around with is the thickness of the material. So the dielectric constant of the film and how much sort of space or gaps there are in that is the ER and the EO. And basically in the brackets there is the bit you're going to play around with, which is the voltage that you're going to throw across this film and its initial thickness. So there's a lot of things like pre-straining that you can do to make it very thin, and other sort of metrics you can play around with. But basically that's your play off in this kind of field activated electroactive polymers. So it's what we're thinking about. And just to show an example of that, so basically this is a VHB double-sided sticky tape pre-strained equally and put across a little plastic disc. So the middle bit where you see the black dot and the two lines off of it, those are the electrodes. And I've painted those on with a petroleum jelly mixed with high quantity amount of carbon black, up to 2 pieces of copper tape where you're going to have your crocodile clips and your power supply off to the side. So what will happen then is basically it will expand and contract radially in and around the size of that electrode. So if I painted a different shaped electrode using the same paintbrush, which I use to apply these electrodes, you can control then where basically the elastomer is going to go. And in doing that, you can introduce more sort of twists, folds, and torsion into the system. So there's a coupling here, I think, between the origami-based things and the dielectric elastomers. So you can use the shape and where you paint the electrodes to control what you're actually going to get as a sort of an end actuation. Okay, so finally I wanted to go through 2 different robotic systems that I've worked on that I think have real potential in looking at these things. And it's this idea of moving away from persistent technology and really getting into sort of full, whole soft-bodied robots that completely decompose. So basically moving from robots as we think about them now to an organism, an artificial organism, where it has its own fuel separate to any need for wires and cables and batteries. And looking at that, we developed one which was powered using microbial fuel cells. So this is not quite like the potato clock, but in the sense of getting an electrical power output from microbes. So you can use microbes themselves to consume food product, and in this case actually consume the artificial muscles that we made for it, so it could sort of cannibalize itself and get power. And microbial fuel cells are still under development, but you can make them from all different sorts of materials. We won't go into the science of the microbial fuel cell, but just to think, when you're thinking about your structures as well, don't get stuck in it all having to be powered by a power source and an Arduino and all the rest of it. You can also think about different ways where it could maybe the power itself could come from somewhere else, and or you could use your materials to be part of the fuel. So thinking of a whole life cycle and back to biology and how well it uses the decomposition products of the higher generations to feed or fuel the development of its young. Okay, so microbial fuel cells that we use still had little bits of wire stuck out of them, but we came up with some really nice different sort of materials. And I want to show just a few of those here. So this is where if you try and think of the robots as being a system, and you can start to play around with what's its fuel, how does it move, and what's its structure. So biodegradable materials could also be used here as a fuel source to power it, and the actuation then it had to be made with the same materials. And obviously we were incorporating the power generated by the microbial fuel cell, or trying to anyway, to get an actuation out. The materials as well, a really interesting thing about biodegradability is it's not necessarily an easy thing to do. Biodegradable plastics can last or persist for years at a time, or some materials can persist until they reach a certain temperature. So the thing to look out for in terms of that or sustainability is thinking about, okay, what can it go on my compost heap at home, or do I need to actually take this to a specific recycling center? So we looked at natural rubbers, which do have a very small use in terms of they can biodegrade and microbes can actually use them and incorporate them. So the actuation of them provided a lot of useful sort of studies because we could get quite a good strain rate from them, but also they could decompose. You'll see there little slides with natural rubber on them by sort of 25 days to a month and be completely gone by about 200 days. The thing about transience as well, I put up a picture of a snowman because someone had laughingly joked that they'd solved the biodegradable issue because here was a non-persistent robot. And it's true, there are materials which can just sort of fall apart or disintegrate, but it's really important to think about the full life cycle back in the environment. So another actuation material that is fun to play with, and I highly recommend in terms of looking at sort of swollen polymer systems or anionic actuation, is the use of gelatin as an actuator. Basically, like you would make jello, you could mix different components into the gelatin itself. You could cool it, you can rehydrate it, and you can allow it to dry again. So there's this nice use to the material. So basically, when I was actuating this in a small sodium hydroxide mixture, I can get movement in an electrical field which has quite large movements in around a minute. So it's a very slow actuator in terms of soft robotics and actuators for use in a robotic system. This would not really do very well. But in other fields, it may be of more interest. And one of the nice things about gelatins, agars, any material like that is that it has a very fluid, natural motion to it. So you can really see it being incorporated into different sort of end uses that maybe not have to be quite so rigid. Okay, finally, the other project that we worked on was in developing a swimming robot. And I wanted to just bring this one up because I think it's a really fascinating way. So the robot itself has mechanical parts. It's not all soft, but using the soft component allowed it to harness energy in the flow. So allowed it to actually mimic fish motion and allow there to be a movement in and around the fluids, which provided thrust and also allowed the robot itself to propel itself in the fluid. So the last part of that I would like to highlight is that we incorporated, so here you have this swimming sort of fish-like structure, and then to be able to put flexible sensors on a flexible moving body, we're really starting to get to this sort of, fully soft robotic system. So here we could put on little artificial sensors, flow sensors all around the body of the swimming fish robot. We could change the design and the array density to sort of allow there to be this feedback and allow the, let's say, full fish organism or artificial organism that we have here to be able to swim, incorporate information from the flow it's in, and continue on. And for me, that's really interesting in terms of being able to feedback into the biological understanding of what is the behavioral reason for fish to draft behind certain places. So we may see that it's not only they hide behind a rock because the flow is slow or that there's more food information from upstream, but also that they're trying to harness the energy and the surrounding vortices generated behind, let's say, bluff body objects in the flow. So this ability to go from sort of materials into a full functioning robot is really fascinating, and also keeping it biodegradable would be ideal. So with that, I was just going to leave you with a little fish robot picture there, and I'd like to take some questions then before passing you on to Adriana, who's going to go through in a lot more detail different aspects of those different actuators and some more as well.
Any questions?
Hi. Can you hear me?
Yes.
I was wondering about the monofilament coils. Do you know if it's important that that's like a nylon, or would any kind of monofilament work?
It's
Nylon.
really important. Yeah, it's really
Okay.
important that it is a nylon or a polyethylene because
Okay.
it has to do with the crystalline structure and
Okay.
how it's going to react and basically allow the thermal activation to occur.
Okay.
But inherent in coiling something is a spring.
Mhm.
Right? So don't let me restrict your thinking process on that, because obviously by curling something up, you could have a kind of an origami effect as well. You're going to
Okay.
accordion something.
You said polyethylene was the other?
Yes. Please.
Okay.
And
Thank you.
nylon 6,6 is a nice one.
Okay. Thank you.
Excellent. Well, if there's no more questions, then I will pass over to Adriana, and I will, yes, where to start?
Yeah, perfect. Okay, I will stop recording.